Hey, as promised, today I'm going to do another circuit example with KVL and KCL applications. I think this one's going to be just a little bit more complicated than what I've done so far, and I'm going to use actual resistors instead of general circuit elements. So let me go ahead and draw up a circuit. Okay, this is the example circuit I'm going to use this time. Let me walk through what I've drawn out so far. I have an independent current source on the far left here, and I'm labeling this current IX. I have two resistors then here in parallel with the current source. One is 5 ohms, one is 2 ohms, and I'm saying that the voltage across the 5 ohm resistor is called Vn, and there's this current entering the 2 ohm resistor that I'm calling In. Then over here, there is a voltage-controlled current source here, denoted by the arrow in the diamond, and it's related to the voltage Vn by this constant A, which I've labeled is 25 Siemens, which is this unit that will convert a voltage to a current. And this source is in parallel with two more resistors that I have labeled here, 32 and 16 ohms. You might be asking, this is a little peculiar because why did I choose to label these voltages and currents Vn and In? The reality is this circuit is actually modeling a real system. So this is a very simple model that you might use to describe a loudspeaker system, where over here on the left we have some input current, and this resistor here, the input, might represent the microphone, and then on the far right over here, this 16 ohm resistor would represent the loudspeaker, and we would call this a load. And then these three elements in between, these two resistors and this current source here, are modeling an amplifier. And now you don't need to know any of that for the sake of this problem. When it comes to looking at a real system and building a model for it, that's one skill. But then actually looking at a circuit and analyzing it, that's another skill. So you don't actually have to know anything about a real system to analyze this. This is just a circuit. Someone created this circuit to model a real system. And again, your circuit analysis tools and fundamentals are all perfectly valid, even if you have no idea what this represents. But I just wanted to explain that a little bit because I did choose to label that this way. So with that out of the way, let me pose a question about this circuit, and we will analyze it. So I'm going to say, given there's a 16 watt power dissipation in the 16 ohm resistor, or the load, or the loudspeaker in the example that I gave. Given that we know this is consuming 16 watts of power, so in that 16 ohm resistor, what is Ix? So I'm asking, if you know how much power is being drawn by our load here, what is this source current, or what is this input current stimulating this circuit and generating the 16 watt power consumption all the way over here? Okay, well in this case, it's really hard to start anywhere except the load. So we're given the power. And that means that we actually have complete information about its voltage and current as well, because if you know a power in a resistor, that actually automatically tells you both its voltage and its current by virtue of the fact that you know the resistance itself. So remember that power in a circuit element is its IV product, or if it's a resistor, it's also I squared times R, and it's also V squared over R. And so we can work backwards with either of these two formulations. and generate an expression for, let's say, current in terms of power and resistance. And this is actually really easy because we've been given that 16 watts and 16 ohms. So it's probably easy for you to notice that I squared is going to be equal to the ratio of P to R, or power to resistance. And because that ratio is 16 divided by 16, or 1, I squared is just the same as I. So really, we can see easily that the current in this resistance is just 1 amp. So if before I draw it in there, how do I know what direction the current is flowing? Now, I don't have to know. I can draw an arrow with a current, and then the polarities and reference directions will work out later, but I actually already know. And let me explain how I know. This dependent current source is forcing current out of it in this direction. We know that for sure. We know for sure there's current coming to the right over here, and then it gets to these two resistors. And because however much current enters must also leave this node, we know that there has to be current traveling in this downward direction through at least one of these resistors. Right? One or both of these resistors has current flowing in the downward direction. But the fact that at least one of them has current flowing in that direction actually proves that they both do. Because if you think about the fact that you'll have current flowing through one of these resistors, that will mean, if the current flows downward, that will mean that the positive polarity of the voltage will be on the top side of whichever resistor has the current flowing through it, by virtue of the fact that it's a passive element, must be consuming power, current therefore must be entering the positive terminal. And so we therefore know the voltage on at least one of the resistors has the positive polarity on the top side. But then, of course, we automatically know the voltage polarity of the other resistor because they're in parallel, and they must in fact share the same voltage because they're shorted together on both sides by ideal conductors. So then I can write, for sure, I know that the current in both of these resistors is flowing downward because I know that they both have the same voltage, which is positive on top and negative on the bottom, and they're both passive, and therefore they consume power, and therefore the current in each of them must flow into their positive terminals. So I can say automatically I know the current in this resistor flows downward this direction, and it has a 1 amp magnitude. Now the natural thing is to say, let's complete our information about this circuit element. We know its power, we know its resistance, we know its current. Now let's write in its voltage, which is also easy because if you look at our P equals IV expression, we have P of 16 watts, I of 1 amp. So if you do a quick division there, it's clear that the voltage is 16 volts. So I'm going to go ahead and write the polarity like this. As I just described, I already know the polarity. So this is 16 volts here. And of course that 16 volts must also be across this 32 ohm resistor because they're in parallel as I just described, and I won't write that again, but they share that voltage. They're just connected by the ideal conductors. And because we know the voltage across this resistance here, we therefore know its current. And Ohm's law says that V equals IR, or I is the ratio of voltage to resistance. So this current coming down this way must be 1/2 of an amp. And this is also interesting. I like this example. I didn't plan on this, but this is a good point here. Notice that the voltage across these two resistors is the same, but one resistor is double the resistance of the other, and it just so happens that the resistor of double the resistance is carrying half the current. And now that should be, I know I didn't explain that, and it's just a consequence of the algebra, but it also has physical significance, and this is where you build intuition here, because what does resistance mean? Why are we using that word resistance? Well, look, current follows, and you might have heard this expression before, current follows the path of least resistance, or current will flow depending on how much resistance it faces. So look, if you have two paths available and some total amount of current that's going to flow here, the path that has twice the resistance of the other has half the current, or rather the path that has double the conductance has double the current. Remember when I described the relationship between resistance and conductance, they're just in inverse of each other. So saying that 32 ohms is twice the resistance of 16 ohms, I could equally say 16 ohms is twice the conductance of 32 ohms. And now this is kind of an aside. I'm going to do an in-depth video on resistances and how they behave in parallel according to their currents, and how you can start modeling combinations of resistances and equivalent resistances in parallel and series. And so that'll be its own video, but this is kind of a sneak peek at that. Okay, now to get back to the problem, now you should be pretty good at KCL by now, and it should be easy for you to see that because there's a half an amp coming down this way and 1 amp coming this way, we actually know the current coming in here must be those two summed together, and this is just the current coming from the source. So it's easy for us to see that the current coming out of this source is 3 or 1.3 over 2 or 1.5 amps. Okay, now this is great. Given that we know the gain ratio here, or the scale factor here, A, and we know the current, then we actually know Vn. And that's because this current is this function. We know that 3 over 2 is equal to this function here, A times Vn, or equivalently Vn, and remember A is 25, so Vn equals 3 over 50 volts. Okay. Now look back over here. We have total information about the right half of the circuit, and now we've just learned Vn. And ultimately we want Ix, so I think it's in our best interests to solve for the currents in these two resistors, and then a KCL will give us a quick answer. So given that we know Vn, we actually automatically know the other voltage, because again these two resistors are in parallel, so you see Vn across them both. So given Vn across 5 ohms, that'll just be an I equals the ratio of V to R to get the current, and then the same for over here. So I'm just going to label this current coming down here quickly. I'm going to call it I1, let's say. And again, I know the direction of this current for the same reason I described over here. I know the direction of this current. I know both currents are flowing downwards into these two resistors here. And I also know the polarity across the 2 ohm resistor to be the same as Vn because it is Vn. And so now let me write this out. I'm going to say I1 equals Vn divided by 5 ohms. Therefore, I1 equals 3 over 250 amps. Now I can solve for the current In, which I know In will be equal to Vn over 2 ohms, which is 3 over 100 amps. Okay, now by a KCL, I know that the currents leaving this node, I1 and In, must be equal to the total current that entered that node at Ix. So Ix will just be the sum of these two. So therefore, Ix equals I1 plus In, which equals, and I'm going to normalize the denominators here, so I'm going to say 6 over 500 plus 15 over 500 equals 21 over 500 amps, or usually, usually in engineering, we'll make this the easiest to write or look at possible. So I will approximate this to it's very close to 40 milliamps. So a milliamp is 1/1000th of an amp. That's what the unit prefix milli means. And so if this were 20 over 500, it would be exactly 40 milliamps. 21 is very close to 40 milliamps, and that's what this squiggly equal sign means. And either of these is fine. Like, look, depending on the class you're in, they'll want the exact answer. If I'm at work and I'm analyzing circuits and I'm running simulations, and someone asks me a question, hey, what's your source current here? I'm just going to say 40 milliamps. So just to give you an idea, that is the solution to this problem. I asked, what is IX? Next, I think, depending on how long it takes, I'm going to add the power calculations for each part of this circuit just to prove to you that this calculation is correct. So let me set up and go ahead and do that. Okay, so I was planning on doing the explicit power calculations for each element here on each half of the circuit. And you can do that. I encourage you to do that if you really don't trust me. But I realized that in this example, it's actually pretty easy to just kind of intuitively see that power is conserved here. And let me explain why. What we have are essentially two different groups of parallel circuits. And it's easy to see when all these elements are in parallel like this. So first look at the right half of the circuit here. We know this 16 volts is across this resistor, and also this dependent current source, because they're all in parallel. So we know the voltage across this current source, and we know it's current. And we also know that the total current entering these resistors is the current leaving this current source, and also that these resistors share the same voltage. So I guess what I'm saying is, look, you have the same current from the source in both of these resistors, and you have the same voltage across the resistors that you do across the source. So at least in my view, it seems very trivial to walk through these calculations, because if you just look at IV products, you have the same IV product across the source that you do across the resistors, except one's negative, one's positive. And then I can make the same argument over here. There's really no added information here if I step through the individual power calculations, because the way I got there, the way I determined the individual voltages and currents was really only one step. Because I have a parallel circuit here, I essentially did the power calculation already. The second I found the voltage, I essentially experienced the one possibility for failure that I have in this circuit, meaning that, you know, stepping through the power calculations in this case, it really just feels like a blind computation, and it will be incorrect or correct depending on whatever voltage I pick here, and so it seems in this case like it's kind of silly, and I encourage you to look for that in your circuit examples, or in your circuit solutions, or in your homework problems, or whatever you're doing for your class, or if you're just doing this as a hobby. You know, you'll start to pick up little bits of intuition like that. Anyway, I hope that was helpful. And if there's anything I can do to improve these videos, please let me know. I'm thinking there might be one more example video that I do after this on KVL, KCL with resistors. And then I'm actually just going to do more circuit element discussion of resistors themselves. So on that note, thank you for watching and have a great day.